Oh, hey, BioBites here, Roy Trebeline. Just producing a little carbonic acid, similar to what we're seeing in the oceans. If you don't recall, carbon dioxide is building up in the atmosphere and it's causing the oceans to acidify. We're doing this reaction up here, right? This weak acid is causing the oceans to become a lower pH. And a lot of the animals can't handle that. Now remember, it's powers of 10 when we talk pH. So if you go even one number down, you're talking 10 times greater the amount of hydrogen. Anyway, let's take a look here. Let's start from the beginning. So I got my little beaker here, and what I've done is I've enlarged my beaker to be the bottom of this whiteboard, right? What was in my beaker was just plain old water. So let's count them up here. When water dissociates, we get hydrogen and hydroxide. It's a simplified, I know it's supposed to be hydronium, but that's all right. So we got hydrogen and hydroxide. We got 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. What's the pH? Neutral. There's 7 hydrogen and 7 hydroxide. Now obviously there'd be a lot more in that beaker, but you get the idea. The minute I add more hydrogen, it becomes acidic. The minute I add more hydroxide, it becomes basic. And the beautiful thing about water, one of the best qualities of water, is it has equal amount of hydrogen and hydroxide when it dissociates, when it breaks apart. So its pH is 7. Our body's about 70% water, and most of our proteins are going to make it at about 7 or their range. There's a couple of exceptions, but somewhere towards the middle. The extremes are hard, right? So if I was to add, for example, a strong acid, oh, Mr. Trebeline, know any strong acids? Yeah. Just off the top of your head?
Orange?
Stronger than that. But although orange is acidic. How about hydrochloric acid?
Oh, yeah.
Hydrochloric acid is HCl. Put it in water and look what it does. It puts all these hydrogen into the beaker, right? It's no longer water in that beaker. It's what? It's an acid. It's got more hydrogen than it does hydroxide. If there's more hydrogen than hydroxide, it becomes a lower pH, 1 through 6, right? It's a log number, that pH. It stands for the power of hydrogen. So if it's a pH of 10, we say it's 10 to the negative 10 hydrogen concentration. In other words, 1 in 10 to the negative 10 is going to be the number of hydrogen found in the solution. And this always has to equal 14. So if the hydrogen is 10 to the negative 10, then the hydroxide solution is going to be 10 to the negative 4. It's a ratio between the two. The pH always stands for the hydrogen concentration. Mrs. Trebeline looks confused. Let's try another one.
So if the blue, those things are 10, there's 10 of them. Should there only be 4 of the yellow guys?
Yeah, for this analogy, that would work.
Okay.
Sure. It's a little more complicated, but that's good. So what if it was a pH of 3? Well, pH of 3 stands for the power of hydrogen. So the hydrogen concentration is 10 to the negative 3. It's a negative log. And so the hydroxide concentration is going to be 10 to the negative
11.
Now, 10 to the negative 11 is going to be a much smaller number than 10 to the negative 3, right? Remember how that works? Okay. So that means there's more hydrogen than there is hydroxide. A pH of 3 is going to be very acidic. We put a lot more hydrogen into the solution. Stay with me. So let's go a higher number now. Let's do a pH as we have up here. Let's do a pH of 10, right? Now I get this 10 to the negative 10 hydrogen, a very small number, compared to a hydroxide solution of a 10 to the negative 4. This number is much bigger than this number. What do you want me to put up this time? Am I putting up more hydrogen or more hydroxide in my beaker if it's a pH of 10? Now remember, to be a base, you got to add more hydroxides. What do you want up there?
More hydroxides.
You want more hydroxides. So for example, if I add sodium hydroxide to my little beaker here, it's going to disassociate and produce all of these hydroxides. Now my solution is not going to be acidic, it's going to be basic. The more hydroxides I got up there, the more basic it's going to be. Now, if you look, these hydroxides have a negative ion. A negative charge on there is gonna want electrons. People make this mistake, but if I stick my hand in a strong base, right? Not an acid, but a strong base, these things will attack my hand just as much as the hydrogen will, right? Where they want to be happy is here at water, where there's equal number of hydrogen, equal number of hydroxide, they form back together and become water. Extreme pHs, whether there's more hydrogen or more hydroxide, are going to be desperate for reacting with anything that gets stuck in it. Strong acids burn as well as strong bases. Now, Mrs. Treveline tells me, I've never done this, but she says, ooh, oven cleaner, you better wear gloves, right? It'll burn your skin right off. It's a strong base. What's it got in there? A lot of what?
Soda.
A lot of hydroxides. Now, in our body, we work with a lot of things called buffers. By definition, buffers are either weak acids or weak bases. This one I just did in the beaker, when I blew into the beaker, is a substance called carbon dioxide. And when carbon dioxide reacts with water, it produces this carbonic acid. Carbonic acid dissociates into these two materials. I'm adding more H's to the solution. Not more bases, but more H's. So we're going to say that that is a weak acid. The reason it's a weak acid is it goes back and forth. So in this case, I'm adding hydrogen to the beaker. What do you want me to put in my beaker this time? More hydrogen or more hydroxide?
More hydrogen.
More hydrogen. The solution becomes acidic. You get the idea. Questions? How are we doing on time?
7 minutes.
Now, the opposite is true. If I want a weak base, if we look at this second reaction, in this second reaction is a weak base. I got ammonia and ammonium, and look at what they're doing this time. They're taking the hydrogen from the solution. Watch what I'm doing here now. I'm taking these hydrogen from the solution, and I'm binding them to this molecule. Mrs. Treveline, if I take away a bunch of the hydrogen, I'm going to have more what in my beaker?
Hydroxide.
Hydroxide.
Base.
So this is going to be a base. Most people, not Mrs. Treveline, she's not only beautiful, but she's brilliant, realize that, hey, if I take hydrogen out of the solution, I'm going to be left with a lot of hydroxide. I know I didn't add them, but just by the mere fact of sucking up all the hydrogen, this solution is basic. This is going to be one of the functional groups I'm going to ask you to know. This amine group, it's NH2. This is NH3, I realize, but it's going to suck up hydrogen. And when it sucks up hydrogen, the solution becomes more basic. We're going to call that functional group, that amine group, we're going to call it a base, right?
So this is confusing because if
Yeah.
you add hydrogen,
Go ahead.
it actually is taking away hydrogen.
If you are adding hydrogen to the solution, like this first one,
No, the second one.
second one, I'm sucking them up.
Yeah, but
I'm
it
taking
says
them
plus.
out of here.
And that
Yeah.
plus doesn't mean plus because it's taking
Well,
them
this-
into it.
Yeah, this was in the solution, and now it's not,
Oh.
right? That's why I took them off the board. That's where everybody gets
Well, I
confused.
get that. Yeah, but okay.
Yeah.
So that's what it was on the board, and then you took out the
Took
H.
the hydrogen away because it's in here now, so it's
Yeah.
not making the solution
Yeah.
acidic.
Yeah,
So both those work that way. This
Yeah.
one's adding hydrogen, this one's sucking them up.
I get it.
Oh, good. How are we doing on time?
9 minutes.
So this amine group has an NH2, and its job is to suck up hydrogen. I'm taking hydrogen out of the beaker. Basic or acidic?
Basic.
Basic, right? How about this one though? It's called carboxyl. It's COOH, and that H takes off and adds to the beaker. It becomes COO. Right?
So you
Without the
add
H.
hydrogen, so it's acidic.
And it's acidic, right? Now, amino acids have an amine group and they got a carboxyl group, which makes them almost schizophrenic. On one end, they're acidic, and on one end, they're basic. The amine group is NH2. Oh, I already did that, right? And this group is called the carboxyl. It's COOH. I'm Roy Treveline. This is BioBites. Thank you.
Bye-bye.